There is many ways to program in IT. Today we're gonna see how to load up in memory a dictionary and how to search into it. I'm gonna start for beginner program, really simple. Load up the dictionary in memory and then go through a loop with a loop, go through the dictionary word by word until the end, just to see if a word exists or not. Pretty simple. And then we're gonna improve that. And this is why I put that on my screen today, a performance monitor. In fact, we monitor the CPU and the memory to see if my dictionary grab more memory, how the CPU, what is the charge on the CPU when I do a search, things like that. And then we're gonna improve our programming with a binary search that could be faster than a loop. And then we're gonna improve that binary search to get it more efficient. And then we're gonna improve again, and we're gonna multi-thread because we're gonna see a single thread have a limit, and then we can multi-thread things, and then we're gonna improve again. So beginner will be happy and expert will love this video. You're gonna learn many things here. Let's start with exercises number one. My exercise number one today. Oh, first, let me show you the dictionary. For your information, it's a French dictionary, but for the exercise, it doesn't matter. It could be any language. We really don't care. We just load up words in memory and we will search if the word exists or not. We don't really care about the language. This is my dictionary, and there is near 370,000 words in it. Let's get back to the first program. First program include couple of things, basic things. I'm gonna define a table or array in memory. My array is going to have a maximum number of word. I said 400,000. It's enough to hold a dictionary of 370,000 word. And the maximum length of my words will be 30. I look in my dictionary and there is no word larger than 25, so that will be enough. NBMO, which means number of word, it's just a counter. Every time I'm gonna add a word in my array, I will say, okay, number of word equal 1. I'm gonna add another one. I'll say number of word plus 1 equal 2 now because I have 2 words in my array, and so on until I reach the end of the file with 300 and so on words. This is my function prototype. I'm going to use only 2 functions. Load the dictionary. That function read through the text file I'll show you. Is going to remove the trailing \n at the end, so the line feed, and put that in my tbdic, so the array. Simple search is just a simple search. It's a loop. We're going to see that function later. The main function I will call load dictionary, and the file name I will load this dictionary into memory, and I'm gonna have a loop, and I will search for 6 words. The word absorber, and a word that does not exist. The word manger, a word that does not exist. The word zooplankton, and another word that does not exist. What I want to test here, I want to test a word near the beginning of my dictionary. One exists and one does not. I want to test a word near the middle of my dictionary. One exists, one not, and I want to test one at the end of the dictionary. I put a loop of one because I want to test once when I start, just to make sure everything works fine. And when I know everything works fine, I'm going to increase that to see how much I can do within a certain time frame. Load dictionary. I'm going to give in a file name as parameter, and then I start my variable definition here. I declare a file descriptor and the current word. I'm going to work with a current word, and then if the current word is good, I'm going to put that in my array. I will read the current word and add it up, and so on and so on. I start with the number of words 0. This is the way to loop on a file. We loop while fget means file get string, fget s. In that file descriptor, the maximum length of 30, put that in current word. This is my current word, and do that until you can read. The moment you will no longer be able to read is because you are at the end of the file. Stop the loop. For every word you found in my dictionary, check if you have a \n at the end. If you have a \n or a line feed or the end of line character, remove it from the string. So go at the end of the string and replace that \n by a 0. A 0 means the end of the string. Every string in C will end when you reach a null character. A null character is a 0. When the word has been fixed, removing the \n, we just copy that word into our array and we increase number of word. And then we go to the second one, we remove the \n, put that in our array and increase number of word, and so on until we reach the end of the file. At the end, we're gonna show something. We're gonna display something on the screen. The dictionary has been loaded up in memory, and there is that amount of word. I translate that to you. I know it's not. You may not speak French, but it's pretty simple program. So there is not very much text in it. And this is my simple search. So remember, we load up 3,069 word in memory, almost 400,000. And then we have to search if the word absorbe exists in it. Doesn't matter the word. The way we're gonna do it, we're gonna do a for loop from 0, the begin of the list, until we reach the number of words we read in that dictionary. We're gonna do that and set up a flag to false. If the word does not exist and we go through the directory, we never found it, the flag will be false. So we're gonna write to the user, the word blah 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 does not exist. But if the word exists, strcmp, it's a string compare. String compare is looking for the word I give in parameter here, compared to the first word in my dictionary. Is the word, let's imagine I took the word simple. Is the first word in the dictionary is simple? No. Check the second word in the dictionary. No, it's not. Check the third word and go through until you reach a word called simple. And if a word simple exists in my dictionary, you're going to put flag equal true and you break the loop. And here, if flag equal true, you will show to the user the word simple exists. That's all. Pretty simple. This is the first program. Remember, almost for beginner. This is why I explain a little bit more, and then we go through more complex program after to improve our search. I will compile that search example number 1. And let's try our first try. The dictionary has been loaded up in memory, and there is almost 400,000 words. And yes, the first word exists, the second one does not exist. This one exists, this one does not. This one exists, and this one doesn't. So our program work fine, and we can put in Linux the time command just to know how long it takes. I run it, and it takes 69 milliseconds. 67, 68. It's almost the same time every time I run it. It's really fast to load up in memory, uh, almost 400,000 word, and do that kind of search 6 times on it. So I did 6 search in my dictionary, and it took a couple of nanoseconds. Let's say it like that. So let's do a loop for more than that, just to see how it is if I do my loop 500 times. 500 times 6 search will be 3000 search. So I want to load up my dictionary and do 3000 search on it. 5 times 6 search should be 3000 search. We're gonna see now how long it takes to do that. And I will control C on it, and I will redirect the output into /dev/node because I don't want to see the output of this. Now we can see there is no impact on memory loading up a dictionary, but running for 3000 search, one of my core CPU is 100% for 13 seconds. You can see here the Linux assign a processor to run my job, and then here the job has been assigned to another processor, and then the job has been continued on the previous one. This is the way Linux work or other operating system. Let's try another run just to make sure we have an average of 13 seconds. The same thing, no impact on memory. We start on a core, we've been continued on another core. 13 seconds later, the job has ended and the core came back to a idle state. And 3 other core never worked on it because it's a single thread program. We program a single thread. 3000 search, loading up a dictionary, 3000 search, and so on, almost 13 seconds. Let's go with example number 2 now. We're going to improve that with a binary search now. We no longer go through a for loop. We are doing a binary search. The same thing, the same number of word, same kind of array. Load up the dictionary in memory, it's needed. Simple search, we won't use it now. No longer use that. We're going to use a new function, decode search. Decode stands for dichotomic. It's in French. In French, we say dichotomic search, or sometimes we say binary search also. Some people say binary search. The main function will load up we'll call the load up dictionary, and gonna do a loop of 1 because the first time I want to do it once, and then I'm gonna search the same 6 word because I want to compare the same kind of search, same word, just to compare if my search is faster or not. I don't change my word. Load up dictionary, nothing has changed. It's the same thing as the previous one. Simple search, we won't use this one now. Well, now we're going to use deco search or binary search. The way a binary search work, we need three elements: start, end, and middle. Just to facilitate the mathematic for all of us, let's imagine I have 400,000 words in my dictionary. The start is the word number 0. Here, start equals 0. And end equal the number of word minus 1. So if I have 400,000, it start at 0. The last one is 399.99 and 999. And the middle, it's uh, it's 400 minus 0 divided by 2. So the word number 200,000 is in the middle of my dictionary. 0 the start, 400,000 the end, and 200,000 the middle one. And there's something important here. When I do my first search, the simple one, the dictionary it's not necessary to have it sorted alphabetically. But when you do a dictionary, a binary search, you must have it sorted properly, because you're going to see how it works. It's important to sort it first. But my dictionary is already being sorted. Don't worry about that. First, we're going to check if the word we are looking for, you remember, I'm gonna try apple. A apple, it's a fruit. And I need to search in my dictionary if that fruit exists. The first search I'm doing, I'm do a search right in the middle of the dictionary, the word number 200,000. And if my word is greater than that, and that's not the case, apple is lower than the word. Let's imagine right in the middle we have manager. Apple begin by A is lower than manager begin by M. I will check if it's not greater than. Let's check if it's equal. If it's the word apple I'm looking for, it's not. So it's if it's not greater and it's not equal, that means it's lower. And then that means that we are in the beginning of the dictionary, not the end. And then at this moment, I will say, okay, now the end is the middle of the dictionary. So you remember, I start at 0 and at 400,000, and middle is 200,000. And because it's lower than the middle, for sure my word is not on the second part, so I can get rid of 200,000 line in my dictionary in one shot. This is why a binary search is fast, because only a simple search, we get rid of half the dictionary one shot like that. And now we're gonna search from the beginning to the line number 2000. And then the middle now is 100,000. So we're gonna check between between 0 and 200,000, and the new middle is 100,000. We're gonna do the same check now. We're gonna check if the word apple we're looking for is equal or greater than the word at position 100,000, and it's not, it's lower than that. So we get rid of 100,000 word now. So first, the first occurrence of the loop, we get rid of 200,000 word. The second time, we get rid of 100,000 word. The next time, we're gonna get rid of 50,000 word, 25, and so on. Every time we loop, we narrow down where we want to to search our word, and we get rid of thousands of lines. This is why I expect a better performance with that algorithm than the previous one. And this is the end of the program. We're going to display to our user the word exists or the word does not exist, depending if we found it or not. Let's try this one now. Again, I did it only once to make sure my program worked fine. I load up the same number of words, so that's good. And exist, not exist, exist, not exist, exist, not exist. That's fine. I can increase the number of search. I will put 500 to compare with the previous one. 500 loop time 6 search equal 3000 search. You remember with the first algorithm, with 3000 search took 13 seconds. Let's see how is the improvement searching 3000 word with a binary search. It took 43 milliseconds, so pretty fast, pretty fast. Do we have a bug? I don't think so. We have our 3000 line here. It's really fast. Let's see now if we increase that, because it's so fast. I'm gonna put 50,000 time. Do it 50,000 time. .2 second. So fast again. Let's try 600,000 time. Now it took 2 seconds. No impact on memory. A little impact on the CPU. One core reach 100% and it lasts 2 seconds and then get back to normal. Other core do nothing. Let's try it again to make sure. 2.0, 2.0. So on average, it took 2 seconds. Okay, to do. Okay, remember it's a 600,000 iteration time 6. It's 3,600,000 search. We load up a dictionary in memory, 400,000 word, and we search 3,600,000 times in it, and it took 2 seconds. It's pretty fast, but I think we can improve that with my exercise number 3. The difference now, I'm no longer using a 2-dimension array. I'm using a 3-dimension array. I put that here. Instead of having one big list, I want 26 small lists. So imagine you have one big dictionary, you have all the words, and you have 400,000 words in it, and you do your binary search on that. Instead of that, I'm gonna have 26 small directory. My first directory will contain only word begin by A. My second dictionary will contain only words begin by B. And C, D, E, F. I'm gonna have one small dictionary for each letter in the alphabetic order. This is why I want to test. Is my binary search is more performant on a small list? Maybe, but I will have to do one if before the binary search to check what is my first letter in the word I'm looking for. That will have a small impact on load dictionary and a small impact on decode search. Remember, simple search, we don't use it. The main loop is still the same. We're gonna load up the dictionary in memory because we still need it. We're gonna do it once to start, make sure everything is fine. We're gonna search for the same word, no change over there. To load up the dictionary, you remember I said number of word equals 0, but now because I'm gonna have 26 number of word, and because I'm gonna have now 26 list, I can do a loop and say, okay, number of list 0 equals 0, number of list 1 equals 0, number of list 2 equals 0. Instead of that, I do a memset. Memset set up, it put something in memory to set it up. I'm gonna check the size of a hint. I multiply that by 26 and I put 0 in that number of word in memory. I'm gonna put 26 0 one shot, and it's faster than doing a loop. The loop here, it's still the same. We read and go through the dictionary. We remove the trailing \n, and then we're gonna have, I call it a cell, my first dimension on my array. I will take the ASCII code of A minus the ASCII code of A. If the word begin by A, for sure, the current word, the first letter, if it's an A, that will be A minus A. So the ASCII code of A is 65, minus 65 equals 0. The cell will be 0 for that, for every word begin by A. I'm going to put that in cell 0. And I put that cell, that TBD cell, number of word of that cell, I put the current word on in it. If it's B, B minus A equal 1, because the ASCII code of B is 66 and A is 65. So 66 minus 55 is 1. That will be cell number 1. And so on. Cell number 2, 3. So A, B, C, D, I'm going to have one cell for each of them. Each of them is going to have a list of word, the word beginning by A, B, C, or D, and so on. I changed the display because at the end I can't display you have that number of word. I'm gonna say you have 26 small dictionary. Each of them you have that amount of word in it. We're gonna see that later when I will run it. Deco search still work the same way. The difference now is on what list I'm gonna check. Instead of having one list to check, I will just determine the cell. So the user is going to give me a parameter, a word like apple or banana. This time I'm going to take banana. If it's banana, the word we're looking for, the first word of banana, it's B. B minus A equal 1. I'm going to use my cell number 1. So the list 0, it's all word begin by A, but number 1, it's all word begin by B. I know it's big. I know the word begin by B, so I don't really bother about the rest of the dictionary. But the rest here is still the same. We go to 0 in the B list until the end of the B list, and we found the middle, and we chunk half of the dictionary, half of this small dictionary, and then we set back the end and the new middle, and we get rid of the half again, and so on and so on. So that haven't changed. And now let's compile that search, exercise number 3. Exercise number 3, I'm going to pipe it in more because there is more information now displayed on the screen. So the dictionary has been loaded up in memory, and there is 26 cells. The cell number 0 contain everything begin by a A, and there is almost 28,000 word in it. The cell number 1, the letter B, there is 17,000 word in it, and so on. And then the binary search work fine or work the same way it worked before. The first word exists, second one does not, this one exists, does not exist, not. So the program worked fine. We'll continue now with more. We will not test 500 this time because we remember 500 took 500 times 6, 3000 word took 13 seconds. But when we implement a binary search, 500 took so fast. It goes so fast. We increase at 600,000 iteration to have 3,600,000 search. I'm gonna use the same kind of numbers now. 600,000 search, 600,000 iteration times 6. We're gonna check 3,600,000 times. On exercise number 2, the same amount took 2 seconds. Let's see now what is the improvement has been done with that way of doing it. Instead of 2 seconds now we have 1.3. Let's do it a couple of times. 1.3, 1.3. So our program now took 1.3 seconds instead of 2 seconds. It's a good improvement, and we can see no impact on memory because we load up the dictionary the same way, or almost. No big impact on CPU. Let's do it again. 1.3 seconds again. No, the CPU one core is working, but the rest doesn't do nothing. So let's go with exercise number 4 now. We're going to improve that again. Exercise number 4, I include more header file now because now I want to multi-thread my search, because one of my bottleneck here, because I can improve, but there is a moment I'm single core and the core is reaching 100%. I won't be able to do much than that. Now what I want to do is I want to multi-thread, and you use more core CPU of doing the search in parallel, so it should be faster. I'm gonna load up the dictionary the same way, 26 small dictionary. I have a new function here, go multi-thread. I'm going to show you that function later, but load dictionary, simple search, and deco search is still the same. I won't go on this one because I already know it. Before checking the main function, I'm going to show you go multi-thread. Go multi-thread is kind of my previous main function. I don't want to do that in the main function. Now I did a function for that. The main function will multi-thread this one. This is why I put it that way. So the same thing, we're going to do it once in the beginning to make sure everything works fine. And then I'm going to increase that to 600,000. And then we will see if we can go more than that. The main function now. The multi-threading, I can use pthread, but I'm going to do another exercises later with pthread to pthread something. Today, I choose to fork the process. Just before telling you the fork, I want to teach you something about Linux. In Linux, there is many process running at the same time. Not only in Linux, but I'm on the Linux box right now. And each of them has been assigned a unique process ID. Every time you launch a program, you have a process ID, and each process have a parent process. It's not showing up here. The parent process ID. No, this is my PID. This is my personal number. I'm process number 9. My parent that make me live is the process ID number 2. So process ID number 2 has been launched, and process number 2, the parent, the PID number 2, fork or do another method of threading that new process, and that one and that one. You know, when we are at the parent 0, 1, 2, and 3 and so on, we are at the very beginning of booting up our server, where the kernel load up. That was the first process, and the second one was PID number 1 and 2 and 3, and everyone else is child of it. So this is the way it works. Every time we start a process, we have a PID. Let me check only the one owned by Eric. You know, here the computer has been boot up, many process run, and then now process RD are bigger number. And then I can see there is some parent. You know, actually, my bash is PID 5973, and I have a parent that is this one. This is my parent here. So when I connect to my terminal, I was in the GNOME, I click here, and then I get into a bash. This is what this means. So I just want to explain you that to understand my fork now. Now I'm in a process right now. When I will launch my program, I will be assigned a PID, and the first thing I'm gonna do is a fork. Fork, it's like clone me, clone myself, and then the process will be cloned like that. I'm gonna have 2 process, and one of them will receive a new PID, and the new PID will be 0. This is the child. And the only difference between my 2 process is the PID. This is why I said, okay, if I'm the child, because you know right now my 2 program run in memory, but the program I launch it once, and right here, because I clone and I fork it, now I have 2 instances of my program running, and both are running at the same time, and both are in the if statement right now. Both of them. One of them, let's say this one, is going to have the PID 0. It will say, okay, I'm the child. But this one will say, no, I'm not PID 0. And this one will go to the else, I'm the parent. So that's all. We're going to see, we should see on our screen, I'm the child, number 1. I'm going to load up the dictionary and do a search. And the other one will say, I'm the parent. I load up the dictionary and do the search. So now, because of the fork, I'm going to have 2 programs running on 2 different core. And both of them will load the dictionary in memory. And both of them is going to search my 6 word. So I'm going to have 12 search running at the same time now. And that's all. The rest of the program is the same. I don't have to explain that to you. It's the same binary search and so on. Let's compile the exercise number 4. And let's see how it goes. I am the parent. The dictionary, and now it load up the dictionary. 26 small, he search my 6 word, and I see I'm the child, and the child load up the dictionary also, everything, and he do the 6 search. So the program will run fine, and we can see here 1 core, the other one took another core, but it has been changed to another one, and then changed to another one. So I have my two program running like that. Maybe it's this, I'm not sure. Let's go with 600,000 search now. So just to remind you, 600,000 times 6, it's 3,600,000 words, or 6,000,000, 3,600,000 search in the dictionary. But now because we're gonna fork and have twice two process, we're gonna have 7,200,000 search in the dictionary with that kind of things, because one of them will search, will do the 600,000 iteration times 6 is going to do 3,600,000 search, but the child is going to do the same thing at the same time. So both of them will have one core and load up twice the dictionary. They're gonna have each of them one dictionary in memory, and they're gonna search through it at the same time. I'm gonna do 7,200,000 search in parallel. So now that program is twice the previous one. Let's see if it reached 1.3 seconds. My expectation is almost the same because it shouldn't be longer than the previous one. 1.2 second, 1.2 again, almost 1.3, almost the same time. No impact on memory or really low. And the CPU, let me try another one where we can see there is two core running. Here I can see, yeah, you have two core running, and sometimes we being sent to another core, but two of them did not really work, not really involved, I should say, in my search. So this is the a good improvement. We do twice the search instead of 3,600,000 now. We do 7,200,000 in the same time frame. So we improve by two. And you remember we start 13 second for 3,000 search. It's completely ridiculous. Now that we know we can do better than that. But I think we can do more because the CPU is sleeping. Even with this 7 million search, the CPU is sleeping. So I prepare a shell script. The rest I'm gonna do it with a shell script just to have a quick and simple thing. I'm gonna run two times my dictionary, my example number 4. I'm gonna load up two process of this, and you remember those two process will fork a child. So I'm gonna have 4 now. Two parent I start, and both of them will fork a child. So I should have 4 process. So now I should do 14 million search, 14,400,000 search. Let's see if it will took the same time. It took 1.3 seconds, the same time as the previous one. But now you can see there is no more line here. All 4 core has been involved in that search. Let me try it again. 1.3 second again. No impact on memory. All 4 CPU has been brought to 100% because all 4 CPU has been involved searching in my dictionary now, and it took still 1.3 seconds. Let push the machine a little bit more. I'm gonna put 10 of this. So now I'm gonna bring 10 process in memory. Each of those 10 process will fork a child. I'm gonna have 20 I will load up the dictionary 20 times and do 72 million search and see how it goes. For sure, because I have only 4 CPU and I'm gonna have 20 process running, 10 times plus 10 child. It should take longer than 1.3 seconds because I can go more than 4. So some of them will wait because the CPU is busy. They will have to wait a little bit, so it should take longer. Let's try how long it takes. Now we can see an impact on memory. The memory has been filled up a little bit more, and the CPU, all of my core has been involved for 7 seconds, and 7 seconds later the memory has been freed up and CPU returned to idle state. And that's it. I hope you enjoy. Beginners should be satisfied with the first example. More experimented programmers should be happy with the very last thing where we multi-thread things and things like that. Thank you for your audience, for your attention. Have a great day.